Hello guys. Today we're going to be looking at section 8.2, which is arithmetic sequences and partial sums. So we've been looking at sequences in 8.1, and we also looked a little bit at series, which are related to the partial sums that we'll discuss in just a second. But let's just define what it means to have a sequence that is arithmetic. When we have a sequence whose consecutive terms have a common difference, that's called an arithmetic sequence. Okay? And the nice thing about the arithmetic sequence is that when we recognize something as an arithmetic sequence, we can write our explicit and recursive formulas a little bit more easily. So this says a sequence is arithmetic if the difference between the consecutive terms are the same. So what it means to have a common difference, if we have a sequence like this, is that if you take the new term minus the previous term, okay, so again, this is the new term minus the old term, that's going to give you your common difference. The way we often think about it is like going from a sub 1 to a sub 2, what are we adding? But the technical way to do that is to take the new term a sub 1 and subtract the old term. Okay, so that number D is called the common difference of the arithmetic sequence. And what's going to happen is that if you graph an arithmetic sequence, it's going to look like it's linear. Okay, and that common difference D is like the slope of our linear equation. Okay, so when we have an explicit form, when we want to write an arithmetic sequence in explicit form, we're going to take a sub n. We're going to say that a sub n for our rule equals, and then you know how slope-intercept form is y equals mx plus b? Well, we're going to say instead of mx, we're going to say d times n. Remember, in the sequences, our input is n instead of x. And again, if d is like our slope, that's going to be the coefficient of n. And then what we're going to do is add our a sub 0, okay? Not a sub 1, but if there was a term that came before that, what would it be? And so this is going to be the case if n equals 1 is the first term, okay? So if n equals 1 is the first term, then that's what we're going to be able to look at, okay? Now we can also define something, the sequence, arithmetic sequence recursively. So again, we always want to give a rule. So I'm going to say here that a sub 1 is going to equal some sort of number, right? They have to tell you where to start that. And then we're going to say that to get the next term, which is going to be a sub k plus 1, we're going to take the term before it and add d to it. Okay, so that's kind of what we're going to be looking at for arithmetic sequences. So the next thing this does is says to determine if the sequence is arithmetic, and if it is, to find the common difference. So if I look here, I have 4 to 9, which means we're adding 5. 9 to 14, we're adding 5. 14 to 19, adding 5. 19 to 24, adding 5. We're adding the same thing to each piece. So because of that, this is going to be arithmetic. Now the other part of this asks us to find the common difference. Well, this common difference is going to be here. And you might say, we're adding, how is that a common difference? Well, remember, if we take a new term minus an old term, so for example, if we took 9 and subtracted 4, we would get 5, okay? And notice that's that common difference, okay? We'll write rules for them in a bit, but now we're just identifying if things are arithmetic or not. So now let's look here. 1/3 to 2/3, we're adding 1/3. 2/3 to 4/3, we're adding 2/3. I'm not going to go any further. This is not the same, so this is not arithmetic. Okay. So now let's actually write the first 5 terms of the arithmetic sequence, and then we're going to find the common difference and write the nth term of the sequence as a function of n. So notice in this example, they gave us not an explicit formula, but a recursive formula. They're telling us I want to start at 200, and to get to the next term, I'm going to take 20 less than the term that we were dealing with. Okay, so again, this is a recursive rule, just so that we get used to that vocabulary. Okay, and when it says, again, write the nth term of the sequence as a function of n, what that means is write an explicit formula instead. Okay, so again, what we're saying here is that we're saying that if we take the next term, that is going to be the previous term, or I'll say the old term, I guess, minus 20. And we said that when we take the new minus old, that gives us our common difference, or we can just look at this. And so what we're going to do to find the first 5 terms is we're going to start at 200, and now we're going to take that old term and subtract 20 from it. So 200 minus 20 would be 180. Now a sub 3, we take a sub 2 minus 20, so 160. Subtract 20 again, 140. Subtract 20 again, 120. And again, because we always subtracted those each time, that means that our common difference is negative 20. And then to write the explicit rule, we're going to have a sub n. We know that, like, the quote slope unquote of our explicit rule of the arithmetic sequence is going to be negative 20. And now we just need to find where we're going to start. Well, again, a sub 1 was 200. So we don't want to put that here. We're going to put that, like, think about what our a sub 0 term would be. So if we were to have an a sub 0 term, what would that term be? And hopefully you see that that would be 220. And then that's what we would put as our y-intercept type of a thing there. Okay, so that's a little bit about going. Sorry, it said my camera disconnected. Oh boy. So anyway, that would be what our explicit rule is. The next question just asks us to write out the first 5 terms of the arithmetic sequence. That's pretty easy. What we can do is we can start with a sub 1 is 5, so that's a great place to start. And then if our difference is negative 3/4, then I can just keep subtracting 3/4 to find each of my other terms. So 5 minus 3/4 would be 4 1/4, or 17/4. If I subtract another 3/4, that gives me 3 1/2, or 7/2. If I subtract another 3/4, that gives me 2 3/4. And if I subtract another 3/4, that gives me 2. That's all they really need to do. Okay. Just for kicks, guys, let's look at writing an explicit rule. Okay. So if I'm writing an explicit rule, I'm going to have a sub n equals. Now I'm going to write my common difference d as the slope, so negative 3/4 times n, not times x, because our input value is n. And then I need to add what my 0th term would be. So if we're subtracting 3/4 going to the right, we'd be adding 3/4 going to the left. So that would give me 5 3/4 as that 0th term. And so I'll just put that here. Okay. Now for something like number 5, notice that they don't give us the common difference. They don't give us where to start. So what I'm going to do is I want you guys to think about these as ordered pairs, okay? I want you to think about this as n, comma a sub n, where n is like the specific position. So like, is it a sub 4, a sub 4 means that n would be 4. And a sub n is the specific value of that term. So the value of a sub 4 is 16, okay? So if I think about this as a point, an ordered pair, this gives me the ordered pair 4, 16. What would the next ordered pair give us? 10, 46. And why is that helpful to think about it as ordered pairs? Well, remember that this is linear, and through two ordered pairs, what we can do is we can find the slope. So what we're going to do is we're going to use the slope formula with those points to help us find D. Okay? And remember, to find the slope, we're going to take y2 minus y1 over x2 minus x1 and simplify. So this gives me 30 over 6, which is 5. And again, this is really like my D, okay? Then, you guys, it's true that you could work backwards from this a sub 4 to get that. But like, let's say this was a sub 40. You wouldn't want to do that. So let's just kind of talk about what we could do. So if we have a sub n equals d times n plus a sub 0, kind of as our rule for these explicit arithmetic sequences, we can put those different pieces in. So what we're going to do is, we know that our d value is going to be 5. And what we're going to do is we're going to put in a point to help find my a sub 0. So we can either put in 4, 16 or 10, 46. I'm going to use the smaller one. And again, this point means that n is 4, so I'm going to put 4 in for n, and that a sub n is 16. I'll put 16 in for a sub n. Oops. And then I'm trying to find my a sub 0. So I have that 16 equals 20 plus a sub 0. I subtract, I find that negative 4 is my a sub 0. So if I were then to write a rule, it would be that a sub n equals 5n minus 4. And then from there, and I do want you guys to know how to write the explicit rules between 2 points, regardless of if it's asking us for the first 5 terms or not. So I thought I'd get a head start on this. And now that we know that, we can write what the first 5 terms are. I could take 5 times 1 minus 4 to get 1. 5 times 2 minus 4 to get 6. 5 times 3 minus 4 to get 11. 5 times 4 minus 4 to get 16. And 5 times 5 minus 4 to get 21. Okay? And what I like about that is that I can see that a sub 4 is 16, and a sub 4 is 16 here as well. Okay? All right. So then let's, oops, we're not to sum yet. So now this example says the first 2 terms of, oops, let's get it right here, sorry. The first 2 terms of the arithmetic sequence is given. Find the missing term. And so once again, I would rather us not find what the common difference is and then go all the way up to 25. You guys, that's not an efficient way to do things. It's more efficient if we find some sort of a rule. And we can find our rule pretty easily for this case, because it gives us a sub 1 and a sub 2, which are right next to each other. So what would we do to get from a sub 1 to a sub 2? To get from negative 1 to negative 10, we would subtract 9, and that'll be our common difference. Okay. So far in the equation, I have that a sub n equals negative 9 times n, and now I need to know what that y-intercept is. Let's call it that, which is like the a sub 0th term. So one thing that you can for sure do is work backwards from that a sub 1. So if going from a sub 1 to a sub 2, we were subtracting 9, that means that if we go from a sub 1 to a sub 0, we would be adding 9. And so then we would end up with an a sub 0 term of 8. And then that's what's going to go in my constant spot. Okay. Now I'm not going to happy cloud that, but I'm going to box that. And it's nice because now that we have an explicit rule, we can find the value of n for n, or a sub n for anything, not just a sub 25. But that is what it asks us to do. So to find a sub 25, we're going to take negative 9 times 25, and we can add 8. And you can use your calculator to do that. You don't necessarily have to do that in your head. And our result is negative 217. Do not happy cloud just the negative 217. Write what this is as well so that we know the input term and the output term. Okay, so now let's look at example 7 and 8. And in example 7 and 8, we're going to write an explicit formula for a sub n for the arithmetic sequence. Oh, that's fun. We already practiced that together when we did examples 4 and 5. See? Planting the seeds. All right, so in example 7, they give us a sub 1 and they give us d. So this is great news because we know that our equation is going to be a sub n equals 4 times n. And now we just want to know what to add to that. And so what we're going to do is go backwards. And then if I'm adding 4 going forwards, going backwards, I'd be subtracting 4. So that would tell me that a sub 0 is 11. So I get that a sub n equals 4 times n plus 11. Okay. In number 8, here we have 2 different terms. We have a sub 5 and a sub 10. And remember what we practiced is to think about these as ordered pairs, n, a sub n. So our first ordered pair would be 5, 190. And our second ordered pair would be 10, 115. Do you remember what we should do with those points? Let's find the slope. And I'll even call it d instead of m this time. Okay, so I'm going to take think in algebra terms, y2 minus y1 equals x2 minus, over x2 minus x1. And 115 minus 190 is negative 75. 10 minus 5 is 5. And then we can divide those to get negative 15 for d. Okay. Then Mackey's friendly suggestion is to then take a sub n and then equals, think about this equation, d times n plus the a sub 0. And then again, we can put in the slope and one of the points. It's just so familiar to us. You don't have to learn really any new formula. So again, and for d, I'll put negative 15. For n, I'll use, again, this 5. And for a sub n, I'll put 190. And then I'll be looking for my a sub 0. So I'll say that 190 equals negative 75 plus a sub 0. And then to find a sub 0, I'll add 75 to both sides to get that this is 265. And now we have our equation that we're going to have a sub n equals negative 15 times n plus 265. And there we go. I have a little comment. There are times that, like some textbooks, use this idea of a sub n equals a sub 1 plus n minus 1 times d. The reason that I don't use this formula personally with you guys is because I want you to see the linear, like the relationship between a linear equation and an arithmetic sequence. There's a method to my madness. You know y equals mx plus b form. This would be a new equation that you'd have to use. And if you use this form, you end up having to distribute anyway. If you use that for this form, you would be saying, well, first of all, we'd have to find what a sub 1 is. Yeah, it's just kind of a mess. So again, it's like you need a system of equations to use it with this method. That's why this is just such a better method. And that's the way that our answers should be expressed, is in that simplified form. No parentheses, all like terms combined, etc. But I do not use that form that we might see in textbooks because it's one extra formula for you to memorize. That's silly. Okay. So the next example wants us to use the table feature of a graphing calculator to find the first 10 terms of the sequence. And what we can do, let's see, I'm going to put it into, just for fun, I'm going to put it into that sequence form. Sorry about the likes, guys. Okay, I'm going to put it into sequence form. And then I'm going to go into y equals, and I'm going to type in the rule. So my rule would be negative 12.4 n plus 9. And again, you can, that's a little better over here. And so what you can do there is just go to the table set. So second table set, and then we're going to start the table at 1. And the change in table will also be 1. And then if we go to second table, then we can list those specific values. So we could list negative 3.4, negative 15.8, negative 28.2, negative 40.6, negative 53, negative 65.4, put this down here, negative 77.8, negative 90.2, negative 102.6, and negative 115, okay? So those are the first 10 terms. Nice that we didn't have to do a lot of computations, right? You didn't have to go into the sequence mode. You just could have stayed in, like gone to function mode and put it in there as well, but as negative 12.4x plus 9. And then again, with our table, start at 1, change by 1, and you do end up getting the same thing. I just think it's fun to play with the different modes of the graphing calculator. All right. So that's a little bit about arithmetic, sequences. The next thing we're going to do is look at arithmetic, the sum of a finite arithmetic sequence. And so if we want to find the sum of an arithmetic sequence with n terms, this is what we can use. It says the sum of a finite arithmetic sequence with n terms is that this s sub n equals, so like the sum, equals n over 2 times a sub 1 plus a sub n. Now, what I don't love about this is that if we're not starting with the first term, it's not like technically like the real a sub 1, okay? So let me tell you what I like to think about these as. The n, I'm going to think about the number of terms that we are summing or that we are adding together. How many terms are we putting together? Okay. A sub 1 is the first term that we want, okay? Not necessarily the real first term of the sequence, but the first term we want. You'll see what I mean in a minute. And then a sub n is going to be the value of the last term that we want. Okay? So this asks us to find the nth partial sum of the arithmetic sequence. And the nice thing is that it gives us all of these different pieces. And one thing I think is helpful to do when we do this is to write a rule for this. And so that's my suggestion at first is to say, okay, what is a sub n? And remember, we've written explicit rules for the sequences before. So here I'm subtracting 11, subtracting 11, subtracting 11. So my rule is going to involve negative 11n. And then if I think about working backwards, I'd add 11 and I'd get that like my a sub 0 term is 51. So that's my rule. Okay. And they're legit telling us that n equals 10. Again, and what that means is it does want the first 10 terms. So like from a sub 1 to a sub 10, when it just gives you an n value like that. Well, remember, that was one of the things that we needed to know is what is n. So our n value is going to be 10. And then I want us to think about our first term, okay? Again, that first term is what we're going to put in for a sub 1. And in this case, the first term that they want is a sub 1. And we could use the formula to do that, or we can just look at the written sequence and see that that's going to be 40. The last term that we want is going to be the 10th term, a sub 10. Now this one we might have to do a little more work for. That's why I had us find the rule, because it's going to be really easy for me to find the 10th term. I can take our rule and take negative 11 times 10 plus 51. And when we find that, that ends up giving me negative 59. Now that we have n, what we're going to call our first term and our last term, we can put it into this formula. So I don't usually put s sub n, I just put s equals, to be honest. And then I'm going to take n, which is 10 over 2, times the first term, which is 40, plus the last term, which is negative 59. Okay? And then you can just put that in your calculator as far as how to find that. So again, we could take 10 over 2, which is 5. I mean, you could even write it like this, okay? I like putting parentheses around this, even though you don't have to. And then we would take 40 plus negative 59. And that gives me negative 95. So that's my sum. My sum is negative 95. Okay. And I want us to contrast that with what we find in example 11. In example 11, we have something that's in summation notation. We can tell that it's arithmetic because it's a linear rule. Okay, so the explicit rule is linear. So that means that it's arithmetic. And we can use the methods that we just looked at today. Okay, when we're finding n, okay, the n value that we're going to find, a lot of people look at this and they say, oh, well, n is 18, okay? But the issue is that if we went from 1 to 18, that's 18 terms because we're counting 1, 2, 3, 4, all the way up to 18, okay? But if we want to go from 0 to 18, that's actually 19 different terms. So one thing that you could do is subtract these and then add 1. So you could say, okay, 18 minus 0 is 18, plus 1 is 19. That's going to be your n. And the reason is because when we subtract, that counts the distance between the numbers, but not the number itself. So we want to make sure that we include the number 0 itself, the term 0 of 0 itself when we have these pieces. Okay. So now let's look at what we mean by the first term. You guys, our first term here is not going to be a sub 1. Remember, the first term, the a sub 1 in the formula represents the first term that we want. The first term that we want is when k equals 0. So the first term we want is going to be a sub 0. Now remember that this summation includes the rule. So I'm going to take 3 times 0 minus 4 to find that a sub 0, the first term that we care about in our summation. Now we want the last term that we care about in our summation. And this tells us that we're going to find a sub 18. So we'll take 3 times 18 minus 4. 54 minus 4 is 50. And now we have n, a sub 1, and a sub n, and we can put it into the summation formula. N over 2, so 19 over 2, times a sub 1, again, which isn't literally a sub 1. It's the first term we wanted, which was a sub 0, which was negative 4, plus the last term that we wanted, which was 50. And then again, we can put that into the calculator. 19 over 2 times negative 4, plus 50. Nope. And that gives me 437 for the sum. Okay. So this is that S equals 437. Okay. Let's do one more of these that's in summation notation. This one is, we're going to sum from 51 to 100, and we're going to use the rule 7n plus 2. So again, the first thing we can do is find n. And when things are in summation notation, what we can do is we can take 100 minus 51, which is 49, and then add 1, which will be 50. So n is 50. It's a little trick. Now the first term that we want is not a sub 1. The first term that we want is told by this index here that we're going to have a sub 51. And so to find a sub 51, we can take 7 times 51 plus 2, which gives me 359. Now if I find my last term, the last term I care about is this 100. So I'm going to use a sub 100, and I'll take 7 times 100 plus 2, and that gives me 702. Now that I have n, a quote, a sub 1, unquote, and a sub n, I'm going to put that into the formula. So S is going to be 50 over 2 times 359 plus 702. Okay, so we can see that we would take 25, because that's 50 over 2, times 359 plus 702, and that gives us 26,525 for our sum. And we'll just make a note of that S is 26,525. Okay? Knowing these rules is expected. We are not giving you these rules. These are going to have to be memorized, okay? And you do have to know the rules. Now, that being said, we're going to show you how you can check your answer on the graphing calculator, okay? So in number 13, it asks us to use a graphing calculator to find the partial sum, okay? What we're going to do is look at the new operating system. What we can do there is you can either go to Alpha, which is down here, Window, and then this number 2 for summation, okay? Or you can go to Math and then arrow down to 0 for summation. And it's on these new operating systems that things are super handy, okay? Because legit, all we're going to do is type this into the calculator. The first thing that we need is the index of summation, the variable. And I know that this has n, but we can, because it's in function mode, if I push that, it's going to look like x, and that's fine. And then here I'm going to put the 0. I can arrow up to put the 100, and then I can arrow over to put the rule. Now we'd have to be careful. We have to put it in parentheses 8n, which is going to be x plus 3, and then over 16. The reason that you want to do that, you don't just want to put 8x plus 3 over 16 is because we want to divide this whole expression by 16. So you do have to be careful with the parentheses, but it'll give you this value. Okay, so notice that it does tell us that our value is 2,543, oops, now 0.9375. Okay. And then the nice thing about the graphing calculator, remember, is that if it is a repeating decimal, that you can turn it into a fraction, as long as it's not too crazy of a decimal. Sometimes it freaks it out, but you could try. I like things in fraction form instead, especially with the next lesson that we're doing. So you could go to math number 1 fraction, and then you could turn it into the fraction this way. So 40,703 over 16. Okay. This is technically arithmetic. If we rewrote this using by applying the 16 to everything, this would be the same as the summation from 0 to 100 of 8 over 16n, or 1/2 n, plus 3 over 16. And then you could use the rules above for that. You guys, in a test situation, if I wanted you to find the sum, and the sequence is arithmetic, the rule is arithmetic in the summation, they're going to be things that turn out like this, like 11 and 12, that are really pretty. Okay. If you put this in your calculator, if you put this in your calculator and just give me this answer, on a test, I can only give you 1 point because you're using your calculator to get the solution. You're not using the formulas. So you can use a graphing calculator on this upcoming test, but just be aware that you have to show your work. Unfortunately, if you have the old operating system, it's this whole hot mess of a thing. You have to go to sum, and so to do that, you would have to go to the math button, and yes, we want to go to the math button, and then we want to do the list, second stat, and then we go over to math here, and then we can go over to the sum, and then we have to type all of this stuff in, and you can see that that's not going to be very fun to do. Okay, so there really isn't an advantage of having the graphing calculator with a new operating system on this, in my opinion. But if you have the old operating system, let me know. I can try to give you the new operating system. Okay, so let me know if you want to try. I'm going to say downloading. I don't know if that's what it is, even though it's not a like from the internet, to try downloading the new system. Okay. Number 14 is our last example. We get to kind of practice both of these pieces, this arithmetic sequence and then finding the series. It says determine the seating capacity of an auditorium with 36 rows of seats if there are 15 seats in the first row, 18 in the second row, 21 seats in the third row, and so on. One of the nice things, I think, is that it's really nice to have the summation notation when you're dealing with finding the sum, because when you have that, you can tell what's the position of the first term, what's the position of the last term, then get n from that, and then we can use the rule to find the values of the first term we care about and the last term we care about. So that's going to be my suggestion, to find that first. Okay. So this says that there are 15 seats in the first row. So that means that a sub 1 is 15. This means that there are 18 seats in the second row. So a sub 2 is 18. 21 seats in the third row. So a sub 3 is 21. And so if we wrote those, what do you see we're doing to get from one term to the other? We're adding 3, essentially, right? So we're adding 3 here. We're adding 3 here. So that tells us that we have a common difference of 3. Okay. So in the rule, we would have that a sub n equals 3n. And now we would just need to find what the y-intercept, the a sub 0 term is. Well, the nice thing is we know a sub 1, so we could work backwards. And now we can, and I'll put it over here because we have to know what d is first. Now we know that a sub 0 could be 12. So that's going to be our rule, is that a sub n equals 3n plus 12. Okay. Now it wants the summation, so let's think about maybe putting that idea in summation notation. And that's another goal of this section, you guys, is to be able to put things into summation notation. And so since we know that this is our rule, we're going to put 3n plus 12 as our specific rule. Okay. We're starting with the first row, so that means that we're going to start with 1. But where do we end up? Well, it tells us here that we have 36 rows of seats. So that means that we're going to have 36 rows. That n is going to be 36. Okay. And so, I like that idea of being able to write, to take a word problem, a real life problem, and to write that in summation notation. And so to do that, we need to write the rule. Okay. So now let's talk about finding the sum. We need n. There are 36 terms here. You can still use the trick here. 36 minus 1 is 35, plus 1 is 36. The first term we care about, we start with 1. So is a sub 1, which again we already know is 15. And then if we take the last term that we care about, that's going to be a sub 36. So we can use the rule 3 times 36 plus 12. So 108 plus 12 is going to be 120. Okay. So to find my sum, I'm going to take 36n over 2 times 15 plus 120. The first term I care about plus the last term I care about. So try putting that in the calculator to make sure that we get the correct sum. And hopefully you guys are getting 2,430 seats. Again, so I'll put a unit on this sum because it was asking us a specific question. So that's the seating capacity. We can't fit any more people in seats than 2,430. Okay. So that's our 8-2. Sorry about my random hospital recording. Let me know if you guys have any questions. Have a great day.